Okay, today we're going to be talking about centroids. And the centroid is basically the same thing as the center of mass or center of gravity. One way of labeling it is with this symbol here. So if you took honors topics in physics, then we're going to be looking at exactly the same thing, but in a different way. Okay, so and remember that an object will balance if you put the pivot point, which is this person's finger, under the center of mass, center of gravity, centroid. It will balance. The centroid is not over or under, directly over or under the center of the fulcrum, it will fall over. So what is the centroid location used for in physics or statics in engineering, basically? Basically, it's a way of predicting, helping to predict how the forces are going to be interacting on an object that consists of multiple members, and such as truss, which we'll be looking at in a little bit. Okay. So what we're going to do is we're going to be looking at things like I-beams, but just to simplify things, we're going to be looking at what's called the cross section, and we're going to find the centroid of the cross section, and so that's what they're showing you here is that shape that looks like an eye. Strange enough, it's why they're called I-beams. Then that's what the shape that we're going to be looking at. So the centroid of an object can be found. One way would be lines of symmetry. Okay, so here we can draw a line of symmetry on this triangle, mirror image to the left and to the right. I cannot draw one horizontally though, and we know that the centroid would lie somewhere on that line of symmetry, but I can only draw one. On something like a square or a circle, when there are multiple lines of symmetry, the centroid is going to lie at the intersection of those lines, and very frequently it's what you would consider the middle of the object. So again, we're looking at two-dimensional representations of what would probably be a three-dimensional object, or what would be a three-dimensional object in an engineering discipline. Okay, so some formulas. You do not need to memorize these; they're on your equation sheet, but you know some of them are pretty straightforward. So some of them you already know. For the example, this one. Here we've got a square or a rectangle, and basically the x centroid, there's going to be a centroid in the x direction. There's going to be a centroid in the y direction, and then to find the actual location, you would plot it like a graph. So the x centroid is one half of the base length. Okay, so just halfway over, and the y centroid is just one half the height, or basically just halfway up. So no big deal there. So it's in the middle. On something like a triangle, it's a little bit different. The centroid is located. So notice that we're looking at the distance from the y-axis. We're looking the x distance from that, and it is 1/3 of the base over. Okay, from the thick side. That's important because it's 2/3 over from the thin side. Okay. And then from the height, it's the same thing. It's 1/3 up from the thick side, or 2/3 down from the thin side. Okay, and then you could flip this triangle, and they do that in the example of finding a complex centroid, and it's still 1/3 from the thick side, etc., etc. Okay, so from a semicircle, you can draw one line of symmetry, and that would just be down like so. Okay, and then that would just halfway over would be the x centroid, because it's symmetrical. So in this case, the radius is 2 inches. So now the radius is 2 inches, not the diameter. So the x centroid would just be 2 inches because it's halfway across the whole thing, which would be 4 inches. That would be the diameter. And then the y centroid, or the centroid in the y direction here, could be x if they flip this on its side, but is 4r divided by 3 pi. Okay, and so in this case, that is the distance here. So it's 2 inches over and 0.8 inches up. So again, make sure that you're using the radius here, because that is the radius, not the diameter. For more complex shape, you've got to use some equations. This looks really complicated, but it's really not. These big E symbols really just mean add them up, and subscripts and all that. It's not that complicated. Okay, so we're going to figure out the centroid location of a more complex shape. And what we've got is a square with the corner notched off. Okay, so what we're going to do is divide this into simple shapes. Okay, so I've got a rectangle, a square, and a triangle. Okay, determine the reference axis. So what we're going to do is we're going to consider the reference point, this bottom left corner, and that's what you're going to do. So you're going to have your y-axis to be here and your x-axis to be here. Okay, so you're going to reference your x over like so, and your y up from so. Okay. So in order to do this method, you need to be able to calculate the area, and this is something that I'm sure you already know. So the area of a circle is just equal to the side squared, so s squared. The area of a rectangle is just base times height, or width times height, however you want to say it. The area of a triangle is 1/2 base times height. Oops, they jumped a circle first. The area of a circle is equal to pi r squared. So again, notice that that's r for radius, not the diameter. Okay. And so the area of a triangle is 1/2 base times height. Now again, these should be in your equation sheet. If you don't have one for me, it's in the modules. You can find the equation sheet, and it's got all the formulas for the year and more, including these and everything, pretty much everything that you need. So the first thing we're going to do is figure out the area of each shape. So the area of this rectangle here is going to be 3 times 6, because it's 3 and 3 up. Okay, width times height. So 18 inches squared. The area of this triangle is going to be 1/2 times base, which is 3, times height, which is 3. So 1/2 of 9 gives us 4.5 inches squared. Okay, and the area of the square is height, so 3 times 3, and that equals 9 inches squared. Okay, so we've done that. We've got a good setup here. A little bit trickier is to find the location of the centroid and its distance from the reference axis that we're looking at. And again, we're going to look at the x centroid, and then we're going to look at the y centroid. Okay, so this first one, the centroid, is located directly in the middle of this. So the x centroid will be 3 over. Okay, I'm sorry, 1/2 of 3 over, so 1.5. Okay, and the y centroid will be 3 inches up. Okay, from the x-axis. Okay, so that'll be our y centroid location. So now when we look at shape number 2, we got to figure that it's already 3 inches over and 3 inches up from my corner. Okay, from my corner, my reference point. So when we figure out the centroid of this location, then we have to add on the extra distance from this rectangle. Okay, so it's 1/3 over and 1/3 over. This would be, since this is 3 inches, it's 1 inch over. Okay, so finding the x centroid, it's 1 inch over from this shape, and this shape is 3 inches over. So my x centroid is 4 inches over. 4 inches over. My y centroid is this distance to my reference axis. And to know that, I got to know this little chunk here. I need to know this big chunk here. So the big chunk here is 3 inches. The little chunk here is just 1 inch, because it's 1/3 of 3, and so it's 4. Okay. The square Okay, so my centroid is going to be located in the middle of the square. Okay, I got my lines of symmetry here. And so it's just half of the way over and half the way up of that shape. So this is 3.5 inches. So we're half of that over. So we're 1.5 inches over from this shape, and this shape is 3 inches. So this is 3 inches plus 1.5 inches gives me 4.5 inches. That's my X centroid location. And then my Y centroid, it is 1/2 of the height, so 1.5 inches. Now there's no shape for me to add this on because it's already on this axis here that I'm referencing. So it's just 1.5 inches for my Y. Okay. Um, so this is just kind of showing what we did. So if you were confused anything that I said before, take a look at this image here and see if that fixes it. If it doesn't, feel free to email me. Okay. The next thing you do is you multiply the centroid's area times its centroid location. So this xi, so this a means the area of shape 1, area of shape 2, area of shape 3. Okay. X is the x is the x centroid of shape 1, which we said was 1.5 inches over. To get AX1 or AXI, sorry, you multiply these two together and you get the AXI. So they're together just like in algebra. When two things are together, it means multiply them. Okay. So for shape 2, we multiply its area times its x, and you get 18. And for shape 3, we get 40.5. So that's this is a multi-step process if you haven't figured that out yet. Lot of steps. Each individual steps is not too hard. It makes the overall thing not too hard, but you can get messed up in a hurry trying to get confused on this. Okay, and do the same for the Y. So our Y centroids and get that. So I'm not going to go through each individual one here. Okay. Um, The next thing you do is you're going to look at where it has this big sigma symbol on your paper on your worksheet. This is a Greek lower or Greek uppercase S, and it's a sigma. It means add. So anytime you see this big looking thing, it just means add. So this says add up the AXIs. So basically take these and add them up. Okay, in the x direction. Okay, and then it says add up your AYIs, so add them up, okay, and you get, strange enough, the same number, okay. The next thing is what you need to do is add up your areas for the sum of A, so sigma A means add up your areas, so add up your areas, 31.5. Okay. The next thing you need to do to figure out the actual centroid. So here's my y bar. The y bar means the centroid in the y direction. So you're going to take your sum of the AYI, okay, and divide it by the sum of A, and that's going to give you your centroid in the y direction. Okay, you do the same thing for your x direction. Take the sum of AXI divided by the sum of A, and you get the same location. And that's because, notice, it's the same centroid location in the x and y direction. That's because we can draw a line of symmetry that goes evenly through both of them. Okay, so I know that was a lot to do, and the only way this is going to make sense is if you practice this on your own. I've got one more example I need to go through, and that's how to do the same problem in a different way, and perhaps possibly even a little bit simpler of a method. So this can be an advantage to using this method, and it's called the subtractive method. And you're going to use the exact same equations and almost exactly the same process, but you're going to start with a bigger and simpler shape, and you're going to treat the shapes to be removed, okay, the shapes that aren't there, to be negative. Okay, so we're going to use the same shape and we're going to get the same answer, assuming we do it right. And this is how we're going to do. So we're going to determine our reference axes. They're going to be the same as before. Okay. And what we're going to do is we're going to consider that we have two shapes. One is this big square. Okay. And then two is this triangle that isn't really there. Okay. So we're gonna start with doing the big square, and then we're gonna subtract off this little triangle that isn't there. Okay. So the area of shape 1 is going to be base times height, okay, side squared, which is going to be 6 times 6, which is going to be 36 inches squared. Okay, so that's that. Now we're going to look at, and keep in mind that we looked at the total shape, including the part that wasn't there. That's important because that's going to be our positive shape. And then we're going to have a negative shape. We're going to subtract off the part that isn't there. Okay, so we're gonna make that negative. So we've got our triangle, which is again 3 inches by 3 inches. Okay. Now, and so 1/2 base times height gives us negative 4.5 inches. So our total height when we add these together is going to be 31.5 inches, which hopefully would be the same as what we did before. Not the height, but the area. Okay. Next, we need to determine the centroid location of each shape. So the first thing, again, consider that we're looking at this big square as one object, and we're going to figure out where the centroid is. So we've got lines of symmetry that would help us, but we already know it's just in the middle. Okay. So the total width to find my x centroid, the total width is 6. We're going to be halfway over, so it's just 3. Okay. And then my total height is going to be, my total height is 6, but we're going to be halfway up, so that is also 3. So that's going to be my y centroid. They're both going to be 3 for this shape. Okay. Now, the triangle, keep in mind that this triangle is upside down compared to the last triangle we looked at. And so this 1/3 of the base and 1/3 of the height, that references the fatter end, the thicker end. So that's from this side here. We're going to be looking at the distance to on the left side of that, okay, which is different, obviously. So let's look at the x centroid for this, and so let's see. So my total width here is 3 inches. That means I'm 1/3 of that over from the thick end, and that gives me 1 inch here. Now, to figure out the distance from my shape, it's going to be the rest of that 3 inches. So it's 1 inch over to the centroid, and then it's 2 inches over to get from the centroid to the line. So my total x centroid is going to be half. It's going to be 3 inches because this is half of 3. Okay, and so this is 3 inches. And then plus those 2 inches that are as the 2/3 of the way over, and that's going to give us an x centroid of 5 inches. Okay, to do the y centroid, it's going to be 5 for the exact same reason. So again, there's some symmetry located in this shape. Okay. So this is what we did. So it's 3 inches over to the centroid of the square, and 3 inches up from the centroid of the to the centroid of the square, okay, the overall square, and then to the centroid of my triangle. We've got 5 inches over and 5 inches up, just like what we went through just a second ago. Okay, this is when the process gets pretty much identical. So we're going to multiply the a times the x and get ax. So we got 36 inches squared. So this is for shape 1, which is the big square. We get 108. Okay, and then below for the triangle. Notice that I made this negative here. I made this area negative because the shape isn't really there. So I'm going to multiply negative 4.5 times 5, and I'm going to get a negative 22.5. So again, keep in mind the fact that triangle we're subtracting off, we make it negative. Okay, and then for the y, do the same process, get the same answers because of the symmetry. These are identical calculations, basically. Okay, Next, what we're going to do is we're going to add up the AXs, okay, and get the sum of the AX, okay, and we'll add those up and we get 85.5. Then we'll add up the AYs, okay, get the sum of the AYs and get also 85.5. Okay, then we'll add up the areas. Again, note that the area of the triangle is negative because we're subtracting that shape off. So what we're going to do is we're going to add those up and get 31.5 inches squared. The last thing we need to do is take our sum of the AX, the AYI, and divide it by the sum of the A. Okay. So sum of the AY divided by the sum of the A, and we're going to get 2.71. Strangely enough, it's the same answer as what we got before. Okay. And we're going to do the same thing for our X, and we're going to get the exact same answer. Okay. So that was a lot. I get that. So hopefully that makes sense. If not, you might Google centroid of complex shapes, or email me and maybe I can help you. Or I can probably send a video your way that might be helpful, similar to mine, but just explained by a different teacher. Okay. All right. So just to kind of keep in mind, so very, very common in when we build stuff, we use these beams. We can use a C beam, an I beam, a box beam, an L beam, or this is just a solid beam. And so we can think of these as being subtracted off from a box beam. So the L is a box beam minus a rectangle. A C is a box beam or a filled-in beam minus a rectangle. An I beam is a filled-in beam minus two rectangles, and a box beam is a solid beam minus a rectangle. So this is an L beam, an L shape. Okay, or we can think about adding it. It's the sum of these two rectangles, and that would give us the centroid. Okay, so a C channel, we could break this up into three shapes, and add those up together and figure out our centroid. So the centroid is going to be somewhere along this middle axis right here. Or there's a couple of different ways we could add these up and we'd all get the same answer. So this is a little bit different and that's a little bit different. Okay. Box beam, we can add up these shapes and get that, or add up those, etc. And then the I beam we've already kind of we've looked at, so we can use these shapes. Okay. Now, when we're going to be using the centroid of an object to help analyze the structure of a beam in terms of its strength, and so the centroid determines the neutral plane where part of the beam is in compression and part of the beam is in tension. And so compression and tension. So when you push down on a beam, some of it is in compression and some of it is in tension. And the centroid marks out the neutral plane that's neither in compression nor tension. Okay. And that is it. All right. Sorry about the kind of long there, but hopefully that made sense to you. And work on tomorrow or today. You work on the 2.1.1, which is a worksheet on centroids. Give it a go, and good luck.